Let us look at an example of solving linear programming using the simplex method. This particular example is of maximization objective. A firm makes two types of furniture, chairs and tables. The profit contribution from each product as calculated by the accounting department is rupees 20 per chair and rupees 30 per table. Both products are processed on three machines M1, M2 and M3. The time required by each product and the total time available per week on each machine is as given below. So here we have been given that a firm makes two types of furniture, chairs and tables. So let's say this represents chair and this represents table. Now in order to manufacture chairs and table, the raw material for both have to pass through three machines M1, M2 and M3. So let's say this is M1, this is M2, and this is M3. So basically the raw material for manufacturing the chair has to pass through M1, get processed there, then to M2, get processed there, then to M3, and then it gets converted into a chair. Similarly, the raw material for table has to pass through M1, get processed there, M2, get processed there, then M3, get processed there, and then gets converted into a finished table. Now we have been given that each chair gives the company a profit of rupees 20. So profit for each chair is rupees 20, and each table gives a profit of rupees 30. So profit is equal to rupees 30. Now let's proceed further in this example. So the time required by each product and the total time available per week on each machine has been given to us. So to process chair, we require 3 hours of processing on machine M1. So this is 3 hours. 5 hours of processing on machine M2. So this is 5 hours. And 2 hours of processing on machine M3. So this is 2 hours. Similarly, for processing a table, we need 3 hours of processing on machine M1. So 3 hours. 2 hours of processing on machine M2. And 6 hours of processing on machine M3. Now we have also been given that the capacity or the available hours on these three machines is not unlimited. So the available hours per week for machine M1 is 36 hours. For M2 it is 50 hours. And for M3 it is 60 hours. So now as you can see, we have different profitability numbers for the two type of furniture. We have different hours required by chair and table on each of these machines, and we have different number of hours for each of these machines for availability of these machines. So now we have to balance all these, and we have to find the schedule of production in order to maximize the profit. So basically, how many chairs and how many tables should we produce such that these constraints are not violated, and at the same time we can maximize the profit. So let's see how we can solve this example using the simplex method. Now the first step in solving a linear programming problem using the simplex method is to construct an LP model of the problem. So in this example, we have to find out the quantity of chair and table to be produced by the manufacturer such that the profit can be maximized. So let's assume that X1 is the quantity of chair to be manufactured, and X2 is quantity of tables to be manufactured. Now by selling these quantity of chairs and table, the company is going to make profits. Now the objective is to maximize profit, which we'll represent as P. So what is P? Now we have been given that for chairs, profit per chair is rupees 20. So for one chair the profit is rupees 20. So we have assumed the quantity of chairs to be X1. So for X1, how much will be the total profit? So cross multiplication here, let's say this is Y. So Y into 1 is equal to 20x1, or Y is equal to 20x1. So this is the total profit gained by selling X1 number of chairs. Similarly for tables, each table is expected to give a profit of rupees 30. So for one table the profit is rupees 30. Now we have taken the quantity of tables as X2. So for X2, how much is the total profit? Again cross multiplication. So X2 into 30 is equal to 1 into Y. So Y is equal to 30x2. So this is the total profit for tables and chairs. Now the overall profit for the firm will be the total profit obtained by selling X1 number of chairs and X2 number of tables. So profit P is equal to 20x1 plus 30x2, and we have to maximize the profit. So maximize, and this becomes our objective function. Now let us take a look at the constraints that have been given to us. So as shown in this table, what we have been given is that each chair needs 3 hours on machine M1, each table needs 3 hours on machine M1, and the total number of hours for which M1 is available is 36. So if one chair needs 3 hours on machine M1 and we have considered X1 as the quantity of chairs to be manufactured, so then all the chairs will need 3x1 number of hours. Similarly, each table needs 3 hours of processing on machine M1 and the quantity of tables is x2. So the total time needed for x2 tables for processing on machine M1 is 3x2. Now the total time taken by the chairs, that is x1 number of chairs and x2 number of tables, is 3x1 plus 3x2. So 3x1 plus 3x2, and we have been given that the total time available for machine M1 is 36 hours. So this, that is 3x1 plus 3x2, should be less than or equal to 36 hours. Similarly, for machine M2, we'll have 5x1 plus 2x2 is less than equal to 50, and for machine M3, 2x1 plus 6x2 is less than equal to 60. So these are the constraints. And in addition to this, the additional constraint is that x1 and x2 should be greater than or equal to 0. So we have the objective function here as well as the constraints. So this is the LP model that we want to solve using the simplex method. However, in order to apply the simplex method, we have to check that the following two conditions are met. So the first condition is that the right hand side of each of the constraints should be non-negative. So that is met here. All the right hand side are non-negative. The second condition is that each of the decision variables of the problem should be non-negative. So that is also one of the constraints we have added. So now we can proceed to the next step, which is standardization of the problem. So we'll now look at step 2, which is standardization of the problem. This is the LP model that we had obtained in step number 1. Now, in order to solve this using simplex model, we need to convert the constraint inequalities into equations. That means we have to convert the inequalities in such a way that the left hand side becomes equal to the right hand side. So let's take the first constraint. So this is indicating that 3x1 plus 3x2 is less than equal to 36. Now there can be a condition where x1 and x2 are such that the left hand side is equal to 35 hours. Now if it is 35 hours, then we cannot manufacture even a chair or a table because each of them need 3 hours on machine M1 and we only have 1 hour remaining. So then that 1 hour becomes unused capacity. So if we represent the unused capacity at machine M1 by the variable S1, which is a slack variable, then we can rewrite this constraint as 3x1 plus 3x2 plus S1 is equal to 36. Similarly, for machine M2, we can add slack variable S2 representing the unused capacity. So 5x1 plus 2x2 plus s2 is equal to 50. And for the third constraint, we'll add slack variable s3, 2x1 plus 6x2 plus s3 is equal to 60. Now here basically, if x1 and x2, that is the chairs in the table, can consume the entire capacity of 36 hours, then s1 becomes 0. However, if there is no production, that is x1 and x2 are 0, then s1 becomes 36. So basically s1 ranges from 0 to 36. Similarly, S2 ranges from 0 to 50 and S3 ranges from 0 to 60. Now, since we have introduced 3 new variables in the LP model, we need to make sure that these 3 variables are included in the objective function as well. Now, S1, S2 and S3 represent cost which the firm will pay for the unused capacity, which may include electricity cost, idle labor, unused raw material, etc. Now that is a cost which needs to be added to the profit equation. So basically this tends to reduce the profit. However, for our purposes of solving this problem, we will consider the cost of this unused capacity as 0. And this 0 is expressed as the coefficient of these slack variables in the objective function. So our objective function now becomes maximize P, which is equal to 20x1 plus 30x2 plus 0s1 plus 0s2 plus 0s3. And we have to add another constraint, which is x1, x2, s1, s2, s3 are all greater than equal to 0. Now let's move to step number 3, which is to create the simplex table. So the third step is to create the simplex table. Now the first row of the table is called the objective row. They represent the profit or cost per unit of each variable in the objective function. This is also known as the contribution per unit. For example, each unit of chair gives a profit of 20 rupees, while each unit of table gives a profit of 30 rupees. At the same time, we have assumed the cost of unused capacity represented by the slack variables as 0. Hence, we can fill these values in the first row of the simplex table. So, contribution per unit or CJ. So we'll place all the coefficients of the objective function: 20, 30, 0, 0, 0. Now the second row of the table indicates the variables in the problem for which the Cj components have been written in the first row. So 20 was the coefficient of x1, 30 was the coefficient of x2, and so on. So we'll place those variables here. So x1, x2, s1, s2, s3. Now below the second row of the table, the coefficients of variables in the constraints are noted down. So our first constraint is 3x1 plus 3x2 plus S1 is equal to 36. So the coefficient for x1 is 3, for x2 is 3, S1 is 1. Now there is no S2 or S3, so we'll assume the coefficients are 0. Similarly for the second constraint, 5, 2, 0, 1, 0. For third constraint, 2, 6, 0, 0, 1. Now there are some more columns to be added to this simplex table, which we will add after the next step of establishing a basic initial feasible solution. So step number 4 is to establish a basic initial feasible solution. Now let's take an example of solving linear programming using the graphical method. So in graphical method we have the x-axis and the y-axis. Let's say x1 is on the x-axis and x2 is on the y-axis. Now let's say that there are some constraints. Let's say that there are these 3 constraints. So the feasible solution region is this area here. So this feasible solution region is represented by the corner points O, A, B and C. Now once we have identified the feasible solution region, basically we then identify the slope of the objective function line, and starting from the origin, so let's say this is the slope, and then we draw this line passing through the origin. Then we keep on drawing a family of parallel lines like this, and basically moving away from the origin. And the farthest point which the objective function line touches on the feasible solution region, that point becomes the optimal solution. Also, we have established that the optimal point is at one of the corner points of the feasible solution region. So O, A, B, C, generally the optimal point is one of these corner points. And this is the same premise on which the simplex method is based. In this method, we'll start at one of the corner points, and at each step we'll move to an adjacent corner point in such a way that the value of the objective for the iteration improves at every iteration. Now again, this I have represented only considering 2 variables, x1, x2. In our case now we have 5 variables, x1, x2, s1, s2, s3. So this is, realistically for this example, this will be like a 5D kind of a graph. But conceptually, basically for the simplex method, we'll start at the origin, that is we'll consider x1 and x2 as 0, and then we'll keep on moving to the other corner points. So basically what we'll do is we'll consider x1 and x2 equals to 0. So what this means is that there is no production and neither chair nor table are being manufactured. So let's substitute these 2 values in these constraints. So for the first constraint, x1 and x2 are 0. So what we get is s1 is equal to 36. For the second constraint, we get s2 is equal to 50 because x1 and x2 are 0. And for the third constraint, again x1, x2 are 0, so S3 is equal to 60. So in other words, what this means is that none of the chairs or tables are being manufactured. So the entire capacity at machine M1 is unused capacity. Machine M2, same thing, unused capacity. And machine M3 also, everything is unused capacity. So here x1, x2 are 0 and S1, S2, S3 are non-zero. So here the variables, the slack variables which are non-zero, are known as the basic variables, while x1, x2 which are 0 are known as non-basic variables. So with this information now, let us complete the simplex table. So the first column is CB, which represents the coefficients of the current basic variables, which are S1, S2, S3, in the objective function. While the second column is the basis column, which represents the basic variables of the current solution. Now, as per the initial feasible solution, the basic variables are the non-zero variables, which are S1, S2 and S3. Hence, let's note them down in this basis column. So S1, S2, S3. Now the first column represents the coefficients of the current basic variables in the objective function. So S1, S2, S3 all have coefficients as 0. So let's note the coefficients here. Now we need to add another column known as the solution values column and represented by B. Now this column takes the values of the basic variables, that is S1, S2, S3, in the initial basic feasible solution. So S1 is 36, S2 is 50, and S3 is 60. So this completes our simplex table with the basic initial feasible solution. Now the next step is to perform the optimality test on this basic initial feasible solution. So after we have established the initial basic feasible solution, we need to check if this is the optimal solution or not. So now two new rows need to be added to the simplex table. The first row is ZJ. Now elements in the ZJ row represent the decrease in the value of the objective function or profit, which will result if 1 unit of the variable in the jth column is brought into the product mix. So this represents only the decrease. This doesn't represent the net change, only the decrease if 1 unit of the variable is added to the product mix. So basically what we are saying here is that the current solution is that S1 is equal to 36, S2 is equal to 50, and S3 is equal to 60. Now in this solution, if we add 1 unit of chairs or X1, then what will be the decrease in the profit? Only the decrease. Similarly, if we add 1 unit of tables or X2 in the solution, then what will be the change in the objective function? Therefore, Zj values are also known as contribution lost per unit from the introduction of 1 unit of the variable in the jth column into the solution. Now the Zj values for the jth column are obtained by adding the products of elements under that column with the corresponding CB values. So let's say for x1 column, we'll take all these elements 3, 5 and 2, multiply them with the corresponding values in the CB column. So 3 multiplied by 0, 5 multiplied by 0, 2 multiplied by 0, and add those 3 up. So basically what we are doing is 0 multiplied by 3, 0 multiplied by 3 plus 0 multiplied by 5 plus 0 multiplied by 2, and this is equal to 0 plus 0 plus 0, which is 0. So this becomes 0. Let's understand what we are doing here. Of course, we have covered this in detail in the video for step number 5 for simplex method, but let's quickly look at what we are trying to do in this example here. So let's take the first row. Now this is nothing but the first constraint, 3x1 plus 3x2 plus s1 is equal to 36. So 3x1 plus 3x2 plus s1 is equal to 36. Now in our current solution, that is the basic initial feasible solution, x1 and x2 are 0. So that leaves us with s1 is equal to 36. Now by calculating Zj, what we are saying is, what if 1 unit of x1 is introduced in the solution? What is the reduction in the profit? So let's say 1 unit of x1 is introduced in this. So what this will become is 3 multiplied by 1, which is 3. This remains 0 because x2 is 0, plus s1 is equal to 36. So s1 is equal to 36 minus 3. We leave it as this because we want to find out a generic form for the reduction in profit. Now the objective function P is equal to 20x1 plus 30x2 plus 0s1 plus 0s2 plus 0s3. Now with Zj we are only concerned with the reduction, so we will not add 1 here in 20 multiplied by x1 because that is the addition to the profit, and that is actually already referenced in the Cj column. So here what we are concerned is with the profit lost. So we'll ignore these two. Now our S1 is becoming 0 multiplied by 36 minus 3. And then we have the regular 0 S2 plus 0 times S3 and so on. And we can actually write this one as it is. So what this becomes is 0 multiplied by 36 minus 0 multiplied by 3. So this was the original value because S1 was originally equal to 36, right? When x1, x2 were 0, S1 is equal to 36. So the only change now, if we add x1, is that we are reducing the profit by 0 multiplied by 3. What is 0? 0 is the coefficient of S1, which is nothing but this represented here. And what is 3? 3 is the coefficient of x1 in the first constraint, which is represented here. That is why for the first constraint we multiply 3 with 0. Similarly, for the second constraint we'll have 0 from the coefficient of S2 in the objective function and 5 from the coefficient of x1 in the second constraint. So 0 multiplied by 5. Similarly 0 multiplied by 2, and when we add these we get 0. So this is the basic concept of what we are trying to do here. Similarly for x2, 0 multiplied by 3 plus 0 multiplied by 2 plus 0 multiplied by 6, so this is 0. For s1 again 0, for s2 again 0, and for s3 again 0, and the value of b is also 0. So what this is indicating is that the current value of the solution is 0, and which makes sense because x1 and x2 are 0, and 0 multiplied by s1, 0 multiplied by s2, 0 multiplied by s3 is also 0. Now the next row is Cj minus Zj. Let me clean this up. This row is known as the net evaluation row and is obtained by subtracting column wise the Zj values from the Cj values. The value of this row represents the net profit in the value of the objective function for each unit of the column variable being added into the product mix. So the Cj row represents the profit or the contribution per unit if one unit is added into the product mix. As you can see, 20 rupees is the profit for each chair which is manufactured. Similarly, 30 rupees is the profit for each table which is manufactured. And Zj column indicates the loss in profit if one unit is added. So if we subtract Zj value from the Cj value, we get the net profit. So 20 minus 0 is 20, 30 minus 0 is 30, 0 minus 0 is 0, 0 minus 0 is 0, 0 minus 0, 0. Now this row Cj minus Zj determines whether or not the current solution is optimal. A positive value in the Cj minus Zj row indicates the amount by which the profit will be increased if a unit of the variable is introduced in the solution. However, a negative value will indicate the amount by which the profit will be decreased if a unit of corresponding variable is introduced in the solution. So in case all the values are negative or 0, the current solution is optimal because there is nothing you can do to increase the profit. Whatever product you introduce in the solution will only decrease the profits. And in case any element is positive, then the current solution is not optimal and there is scope for improvement. So in this example, since the value of Cj minus Zj for the columns x1 and x2 are positive, the solution is not optimal and there is scope for improvement. Hence we need to proceed to the next step, which is to improve the current solution.